Hi everybody, what I'm going to do in this video is to introduce you to the missing part of physics. It's been with us for about 40 years and it's sat in front of us in plain sight, unrecognized. Nobody knows what to do with it. Now if you watched the first two videos, you'll have seen that we came to the conclusion that we had to use a common cause of action for every action in the universe. The exchange of information. And by doing that, we can now reveal the missing part of physics as a set of laws as fundamental as classical physics and quantum physics. They describe the behavior of physical matter, and they are fundamental. They do not emerge from classical physics, just as classical physics does not emerge from quantum physics. So what are they? They're here. The laws of chaos and non-linear dynamics. Now let's just explain that language to you. What's non-linear dynamics? It just means anything that's not physics, which is all linear, anything that's not chaos, so something like the solar system, which is a self-organizing system, that's not chaotic, or biology, or chemistry. If you're going to understand those, you have to understand these laws first. So let's bring them in from the cold and sit them down alongside the laws of classical physics. This is physical behavior of matter. So we have to have a common cause of action, the exchange of information. So any chaotic system, of course, requires the exchange of information between all the parts. So let's read to you out of the book. Page 3. First page in the book. Why have scientists, engineers and mathematicians become intrigued by chaos? The answer to that question has two parts. 1. The study of chaos has provided new conceptual and theoretical tools enabling us to categorize and understand complex behavior that had confounded previous theories. That means physics. 2. Chaotic behavior seems to be universal. It shows up in mechanical oscillators, physical systems, electrical circuits, lasers, non-linear optical systems, chemical reactions, chemical systems, nerve cells, biology. So if you want to unify physics and biology, you must understand this. Must. So now this can come down and sit beside classical physics as the behavior of matter that produces unique outcomes. Outcomes with possibilities greater than 1. Classical physics only has outcomes which are completely predictable. If you measure the length of the arm of a harmonic pendulum, you know the rate at which it will tick. 2 bodies in space, but no more. Laminar flow. 1 possible outcome. And then you get chaotic behavior. An infinite number of possible outcomes. What a big change. We're going to use that combination of classical physics and chaotic physics, and I'm going to call it physics. Because if it's the description of the behavior of matter, physical matter, and it's fundamental, we've got to say it's physics. But I'm not the person to say that. It's got to be a consensus amongst everybody. Now we know what it is, we can give it a proper name. So that's a big, big change, and we're going to use that change, set of laws which is all predictable, which collapses into an infinite number of outcomes, working as a partnership now to solve the biggest problem in quantum physics, the collapse of the wave function. You see, quantum physics all starts off deterministic, just like classical physics. But if you try and detect a wave in space, the Schrödinger equation, and you introduce another component, a particle detector, where that little dot appears on the screen, you don't detect the wave, you get something else. Where that dot appears is unknowable. But once it has appeared, you've measured it, you can state where it is. Now that's like a coordinate in mathematics. It has no size, it's not physical, but you can state where it is, you can count it. It's that place there. It's defined, it's countable, whereas the wave is not countable. So now we've got a relationship which we've all been waiting for to solve the collapse of the wave function. Deterministic behaviour collapsing into non-deterministic behaviour. Laws of chaos. The harmonic pendulum. Completely predictable. You add one component, another arm, and you get a chaotic pendulum. Completely unpredictable. Turbulence. Completely unpredictable. But air over an aircraft wing, laminar flow, completely predictable. It's a pair of properties working together. And as you've seen with what I quoted from the book, chaos turns up in biology. Now there's a prediction in this book which I'd like to read to you. I recommend that you get a copy of this book, by the way. It's full of all the clues you need to sort out physics. He says the number 4.699, which is one of the Feigenbaum constants, which dictate when chaotic systems will bifurcate and by how much they bifurcate, is destined, we believe, to take its place alongside the fine structure constant of physics. So if we change cause of action to exchange of information, these two can sit side by side. We've done it. That's a big deal, a very big deal. And because chaotic systems are determined only by what happened last, the last action, we see a pattern that shows up in our behavior. It shows up in biology. Asexual reproduction. One possible outcome. Classical physics. The shell lands here. One outcome. Sexual behavior. It's unknowable whether the offspring will be male or female at the individual event, but as a collective we get an even distribution of males and females in the population. Same with chaos. Each event unknowable, but a million events you get a beautiful logistic map which is a one-to-one match with the Mandelbrot set in mathematics. So where does that show up in our behaviour? Classical physics, deterministic. Classical music, deterministic. You play what's written on the score. That's it. Always comes first. Asexual comes first. You can have classical physics by itself, a harmonic pendulum, two bodies in space. It's later that you get the chaotic, unwritten future. Classical music collapses into jazz. Classical art, which ends up as the Pre-Raphaelites, perfect reproductions of nature, collapses into Impressionism and Surrealism. Human behaviour. The male business suit. Females wear whatever you want. Now there's not many YouTube videos which unify quantum physics, classical physics, the laws of chaos, biology, art, music, and human dress code. It's not only the dress code. Think of the male brain. Multitask? No chance. Female brain? Now, this is going to be hard for you to accept. It's so unusual, but it's completely logical. And it takes time to accept information like this. So give yourself time. Watch the video 2, 3, 4 times. Talk to other people. Set up a discussion. Establish a norm. That's how you get over the human resistance to unexpected, unusual outcomes. You've won the lottery. I don't believe it. There's somebody stood there with a cheque. I don't believe it. I can't believe reality. So this video, you're listening to a logical explanation of nature. And if you watch the first 2 videos, it all adds up. It's the same story. And we haven't got to complex self-organizing systems yet, like the solar system. You can't just use physics to explain the solar system. That's often implied by scientists who should know better. So that's going to be the next video. How do you get from chaotic systems, simple systems based on the laws of physics, to self-organizing systems like the solar system? Well, there's a clue. Once again in this book, page 47. It's a very important clue. I'm going to read to you. What has surprised almost everyone is the vast number of common features discovered in the behaviour of non-linear systems. These features include the sequences of bifurcations, connecting regular, periodic behaviour to chaotic behaviour. In this chapter, we'll explore some of the completely unexpected quantitative aspects of these bifurcations. These features seem to be largely independent of the physical, chemical, or biological details of the system under investigation. That is the most important sentence said in a century. These features are independent of physical reality. And that's how nature can go beyond the second law of thermodynamics, which only says that things fall apart, and yet we observe the universe falling together in self-organizing systems, stars and elements, the solar system, chemistry, biology. That needs an explanation. And there you have it. So we'll do the self-organization of systems in the next video, because you need layers and layers of more mathematical rules on top of quantum physics, classical physics, and chaotic physics. We'll see you in the next one. It's going to get interesting.